I just sent you a strongly worded email.
Yeah, I got it. Okay, everybody's here. Yeah, everybody but me. All right. Get folks in here. All right. Yeah, sorry, folks. An interesting question came up, and I lost track of time. Let's see. Okay. Yeah. So, yeah, in quantum, we were doing this delta function potential. So the question is, what happens if you have potential proportional to the derivative of a delta function? And we just spent some time trying to sort that out. So I apologize for starting late here. I had no idea what time it was. I thought I had time for like lunch or something, but I don't.
Well,
so let's see. Yeah. That's, yeah, I bet you do. Let me see now. I have to gather my notes. Still trying to get everybody on the same page here. So let me see. Okay, I don't need that. What I need is the book. And I've posted a bunch more. Just yesterday, I got, let's see, up through, I don't know. I've now edited, well, somewhere into the 90s. So everything in chapter 1 and chapter 2 has been edited at this point. So we were talking about spin representations last time, right? Can you guys remind me exactly what we were saying last? Where had we gotten on that?
we were looking at some hermeticity.
You had showed infinitesimal
no,
rotations.
Yeah. Okay. Infinitesimal rotations. Let's see. And now, did we do that? Did we do SU2? How far? Or SO3? Now here. Right. See, blank looks. So tell me the last thing we did. Have you got it there, somebody?
Yeah,
I think we did SO2. We haven't done SO3 or SU2. I think you wanted us to work on SU2.
Okay. All right. Well, let's look at these. We'll converge on the same page. Oh, nice. All right. Okay. Never mind the second group. Okay, so all right, Lie groups. We're talking about Lie groups here. Now, in Lie groups, the generators can be the group elements are functions of n real variables, and you can expand those infinitesimally. So if I have, say, an n vector, basically I can write this near the identity as 1 plus proportional to those infinitesimals dotted into, for a linear representation, n matrices that characterize the different directions in the tangent space at the identity. Now, these guys always satisfy some commutation relations. There's some constants this is just general overview. We're going to get back to the rotation groups in a minute. We always have this, and then we always have the Jacobi identity. So these are so cyclic permutation of these three. We have a closed commutator algebra, and we have the Jacobi identity. This is an integrability condition, ultimately, that lets us go from the Lie algebra back to the covering group of the Lie group. Then these properties follow from group properties and imply the group properties. So if I exponentiate a general element of the Lie algebra, which is, so these are basis vectors in a vector space. A general element is a linear combination of those. The exponential of those will give me a representation of the group. So we always have these relationships in a Lie algebra. Now, we're particularly interested in a handful of Lie algebras. We're interested in rotation groups, in general, special orthogonal groups in n dimensions, 2 or 3 being most common. But in fact, for space-time, we have 3 spatial and 1 time-like direction. In general, we might be interested in SOPQ, which preserve P plus 1s and Q minus 1s. And this general case follows all the same basic procedures as all the other cases. So many times you might as well just do all SOPQ at once. And each of them has a 2-to-1 cover by a spin group. And that's really what I want to get at here. In particular, SO3 is in a 1-to-2 relationship with elements of SU2. Now, we talked about SO3 a bit last time. Let's refresh ourselves on that. So these basic properties we got the generation. I don't think I proved this, but the Euclidean metric is basically the identity matrix. And if I look at the condition for an orthogonal transformation to preserve that, right, if I write the indices correctly here, I've got O, I, K, O, J, M. Did we do this last time? That better be delta K, M.
Yes, we did.
All right. And since that's the identity, this just means O transpose O needs to be 1. So it's an orthogonal transformation. Its inverse is its transpose. Then expanding these infinitesimally, writing O as 1 plus some W dot J, we found that these J's had to be anti-symmetric matrices. We wrote down 3 anti-symmetric matrices, 0, 0, 1, minus 1, 0, like this, and then the 1 and minus 1 in the other 2 positions. So this one would be J1, I think. Right? You're with me. Okay. So yeah, in fact, we chose these in such a way that Ji was epsilon ijk, give or take a sign. Okay, and that by making that choice, right? That's an anti. So for each I, JK give me an anti-symmetric matrix. So then exponentiating those. Did we exponentiate those? Yeah. Okay. So we got a general rotation of in terms of sines and cosines. All right. And yeah, I remember the final expression. Okay. So now I remember where we were, right? Yeah, that only took the first 20 minutes of class. I apologize. I just completely lost track of time. So did you apply that matrix we derived to a coordinate x? No, you just ignored what I asked you to do, right? You know, that was an assignment. You all failed. Boo. Let's do it.
I did it. I didn't fail that part.
Okay, Alex passed. All right, good, good. Somebody's paying attention in here. You got to do these problems, guys. All right, so Alex, tell me what we got.
Let me find my result. Yeah, you asked us, I think at least for the SO, you asked us to apply it to a vector and then rewrite it in terms of its perpendicular and parallel components.
Yep.
And so I got, sorry, I just wrote it out.
Here, tell me the whole expression. What was the matrix we derived for O?
I'm sorry, the matrix we derived for O.
Yeah, the thing you're going to apply to X.
Oh, yeah, sorry, I was writing that as the G of W, so the action on the vector,
Oh,
sure.
yeah.
And it was yeah, whatever. We ended with 1 minus, and I wrote this in terms of M, which is the squared thing. So 1 minus M plus M cosine of O plus n hat applied to the J vector matrix times sine of O.
Sorry, say the M cosine.
Plus n hat dot J vector. So, and that's the matrix J. Yeah. And then sine of O.
Uh-huh.
And then M is something like, I think M is the delta function minus n M up and then n down and then yeah.
Yeah. Okay.
Yep.
Okay. The sign right on that?
I think so, but
Okay. So this is yeah, this is some nice.
the sign I think is opposite for M. Sorry.
For M. So it's this way?
That way. Yep.
Okay. All right. So so we got that when we exponentiated, you know, we were able to extract M or J and get a just the Taylor series for sine and cosine.
Wait, hold
So-
on. The M matrix, I remember because I have it written down first as a minus plus, and then I scratched it off and changed it as if there was a correction
I think
later on.
I think I changed it in the middle to get the alternating sign and the sine and cosine.
Okay.
But maybe. Yeah.
Let's find out.
We'll see if a sign comes out funny here. But let's apply this to some 3 vector X. You know, this is a 3 by 3 matrix. And that's going to be my rotated X. And so that's going to be, all right, 1 is just going to give me X. Then we get minus, right, we have 1 minus cosine theta here, if I collect that. And then we have this acting on X gives X minus n hat n dot X. Right, when I put this on an xj, I'm going to get an n dot x and so on. And then here, oh, let's see, what is this? Yeah, n hat dot j acting on x sine theta. That's some vector that we better work out. So now n dot j I can write as ni. J is epsilon I j k acting on xk. So I'm looking at this last term, sine of theta. All right, if, well, up to sine, if I interchange these two, I get a minus sign, and then I have n cross x. So this is equal to minus n cross product with x. Sine theta. So that is the the j component of that. So this last term I can write this last term as that minus n hat cross x sine theta. Okay, is everybody with me? So, oh wow, that was, yeah, you're good. Okay, yeah. So maybe, yeah. But all right. Now, what I want to do is introduce a basis. I have n and n cross x here. Let's draw a picture of what we're doing. So we've got some unit axis n. We've got some general vector x. And then if I take n cross x, that's a vector n cross x. That's a vector into the board. Now, let's see. If I write, let's see, n cross x that's the magnitude of n times the magnitude of x times this angle between them. Let's see. I'm not sure if I need that. Let's see, n cross x is into the board. Then if I take n cross x, what direction is that? That's into the board. Then n cross that is a vector this way. So my basis is going to be made up of these two vectors and a vector into the board.
This is very similar to what we were doing for rotating frames, right? This kind of analysis.
For rotating frames, yeah. That's right. Yeah, we did go through very much this. So yeah, now you've seen it twice. Okay, third time's the charm, right? Okay, now, so we want to figure out what this all is. If we write x as a part of x, right, in this basis, there's the part of x that's parallel to n, and then the part perpendicular to n. So how do I write the part perpendicular to n? Well, it's the difference of these. So it's actually that thing right there. This is x perpendicular. And so that is that bit right up there. So then what do we have? This is, let's look at x minus x perpendicular as this first part. And then we have plus, it's going to be, right, this is x perpendicular. So yeah, so I have plus x perpendicular cosine theta. Minus n hat cross x sine theta. Okay, x minus x perpendicular is just x parallel. So then we have the part of x perpendicular times cosine theta minus n cross x. And okay, n cross x is going to kill the part parallel, so I can write this as n cross x perpendicular sine theta. And now you see an ordinary two-dimensional rotation emerging, right? So the part of x parallel to n stays put. Then these two parts, I get x perpendicular is this, and n cross that is the direction perpendicular to both. So what's happening is this last term has magnitude of x perpendicular. This has magnitude of x perpendicular. So we're looking in a plane perpendicular to n, and we're taking cosine of x perpendicular minus sine times the perpendicular part, that's exactly a rotation in that plane. Just the sine and cosine rotation. Everybody nodding enthusiastically? Or, okay, so you see it. If I were to write a rotation in 2 dimensions, it's cosine theta minus sine theta, cos theta. Say x in the xy plane, I would write something like this. You know how to do a rotation in a plane. Well, just take the plane to be that plane perpendicular to n, and this is that expressed in vector notation. Okay, so now we want to do the same thing with SU2. Are there questions on this one? I know I ran through that fast, but you're okay. All right. Kevin, you good? You good? Okay, great. All right, so now let's look at SU2. First off, let's see, did we do the argument that SU2 is the rotation group? We'll get there. Let's let the matrix capital X be defined as a 3-vector dotted into the Pauli matrices. All right, so I can characterize that by saying that X is Hermitian and traceless. I think we made that argument last time. All right, so if I were to write this out, this is going to be z x minus I y, x plus I y, and minus z. All right, so it's that matrix. It's clearly Hermitian, it's clearly traceless, and every traceless Hermitian matrix can be put in that form. So if I preserve these properties of X, then it has to be something that, well, we want to preserve one more thing. Notice that the determinant of X is minus z squared minus x squared minus y squared is minus the length of X squared. So if I preserve these 3 properties, it has to be some sort of rotation. Only a rotation will preserve all of those properties. Preserving these 2 means that I can write the new thing, some x prime is going to still be some real linear combination of the Pauli matrices, because every matrix satisfying these 2 properties can be written in that form with 3 real numbers. If the transformation I do also preserves the determinant, it preserves the length. And so preserving all 3 of these means that x prime squared equals x squared. And it has to be a rotation. So this is a mapping that accomplishes a rotation. It's just like, let's do it. Well, so in order to make it Hermitian, let's consider a transformation of the form ax a dagger to be my x prime. And the determinant of that is the determinant of a times the determinant of a dagger just squares that, and the determinant of x is the determinant of x prime. And that means that the determinant of A, we did all this, right, is just some phase. We argued, oh, a phase here is going to cancel out. It's not going to actually transform X anyway. So those are completely superfluous. So we're going to take the determinant to be 1. And finally, the tracelessness, the trace of a dagger, there's a cyclic property to the trace. I can write that as the trace of, can you see here, a dagger AX. And so if I take a dagger to be a inverse, that becomes the trace of X. This is the trace of X prime, and so that trace is 0. So if I let X prime be AX A dagger, where A dagger equals A inverse and det A equals 1, I've satisfied all 3 of these properties. And that means that I can write X prime as some real linear combination of the Pauli matrices. Well, these 2 properties imply A is an element of the special, that is determinant 1 unitary group in 2 dimensions. All right, 2 dimensions because we're acting on this 2-dimensional matrix. Unitary because A dagger equals A inverse. Special because determinant is 1. So we derive the fact that transformations, elements of SU2 acting on that X by similarity, adjoint similarity, will generate a rotation. Now, we just have to find all of these guys. So I should give you this for homework. It'll do you more good than me, but let's see what these things look like. SU2. How do we write the infinitesimal elements of SU2? So we're going to write an element as near the identity as some vector dotted into generators. And the property we need, let's see. We need determinant 1, we need it to be a Hermitian, unitary. So G dagger is going to be 1 plus W dot G dagger. G inverse is 1 minus W dot G, right? So why is that? If I multiply these, the cross term here vanishes and I get something of 2nd order, and W is infinitesimal because we're looking at infinitesimal transformations. That's 2nd order, so we drop it. Okay. Now, let's see. If I equate these, that's 1 plus W dot G dagger equals 1 minus W dot G dagger. The 1's cancel. W is arbitrary. So if this is true for every W, then I have to have G dagger equal to minus G. So anti-Hermitian. These generators, right? I can take these to be any linear combinations of I times the identity or I times the Pauli matrices. And that's a complete list of the anti-Hermitian matrices because 1 and sigma are all of the Hermitian ones. I just multiply them by I. So now, let's see. What can I erase here? I need the tracelessness. Okay, so I write G as 1 plus, let's see, some linear combination. Well, a linear combination of these things. I'm going to have an I here. And then if I think of G as some alpha, beta, mu, nu, actually, if I pull out the I, it's got to be Hermitian. So I can write G as I times some real number, and just, sorry, complex number, and its conjugate, beta conjugate. So now, if I put that in up here, I have A, beta star, beta, B. So I can write G like that so far, but the if I combine that, I've got 1 plus IA, I beta conjugate, and 1 plus IB. And what did we require? That's the generator, that's the group element, that's the infinitesimal group element. It's got to be traceless, right? Was that a condition? I've lost it.
Yes.
Unit determinant. We've got to have unit determinant. So the determinant of this is going to be 1 plus I, A plus B, minus AB, minus plus beta star, but it's infinitesimal, so I drop the quadratic bits. And I need determinant 1 for it to be special unitary. And that means that B has to be minus A. And now back to my original matrix, this is I times A minus A, beta star. That is a linear combination of the Pauli matrices. Everybody see it? That's sigma Z, and this is sigma X and sigma Y, right? So my generators also have to be linear combinations of the Pauli matrices. So these guys, my G's can just be I sigma. Okay, what can I erase here? There's my X, there's my infinitesimal transformation. So a general element of the Lie algebra is going to be a linear combination of I sigmas. I'm going to write that as an amplitude phi over 2 and a unit vector n dot sigma. So there's my I. I'm writing W as an amplitude phi over 2 times a unit vector n, because I'm allowed to and I know where this is all going. All right. Anybody see at this point why there's the half there?
Is it because we're going to do some sort of a bracket? We're going to get 2 of them.
It's because, yeah, we get 2 of them. X prime is a X, a dagger. We're going to get 2 of these transformations. So a general group transformation is just the exponential of that stuff. And we're going to put 2 of those here. And we're going to get a whole bunch of double angle formulas. So we're really doing 2 rotations by a phi over 2. And this is where we get the 2-to-1 cover. SU2 gives a 2-to-1 cover. There are 2 elements of SU2 that accomplish the same effect as any given element of SO3. So Now you guys want some practice with Pauli matrices? Homework for Wednesday. Work this out. And you better do this or I really will give you all Fs. Right? But yeah, do it for Wednesday. It doesn't take that long, right? But X prime is some real linear combination of the Pauli matrices. And it's given by a X, a dagger, where we now know, right, that this is a general element of the Lie algebra. We get the group by exponentiating it. We work through that. The calculation is the same for any Lie group. It's always the exponential. So A is going to be e to the I phi over 2 n hat dot sigma. X is going to be our original x dot sigma. And what I want you to do is work that out. Now, step 1. You need an identity for these guys. So show, this probably is an exercise, that write out the Taylor series for the exponential, calculate powers of n dot sigma, and show that e to the I phi over 2 n hat dot sigma can be written as the identity times the cosine of phi over 2 plus I n dot sigma times the sine of phi over 2. Step 2, write it all out, right? So x prime.
Wheeler,
Yeah.
step 1.5 is to adjust the screen. There we go.
Okay, we're good. Step 2, all right, you have x prime dot sigma. You take one of these, cos phi over 2 plus I n dot sigma sine phi over 2. But no, that's plus. Then x is x dot sigma, and then the conjugate 1 cos phi over 2 minus I n dot sigma sine phi over 2. Multiply it all out and collect terms. Okay, this means you have to work out, you know, sigma squared and sigma cubed. So let me give you some hints on that. All right, if I have to multiply n dot sigma yeah, so suppose I had to square that. This is one of the things you're going to have to do. Use index notation, ni sigma I nj sigma j. Here, let's keep it proper here. So this is ni nj. What is sigma I sigma j? I want the product of any two Pauli matrices.
It's direct delta. No.
No, they're just matrices.
Yeah.
Okay, so step 0. Prove that
Oh yeah, they're
sigma
like
I,
the
sigma j,
quaternions.
right? They square to 1. So delta 1 times the identity, and then they cycle epsilon I j k times I times sigma k. It's all Euclidean, so indices up or down won't matter. But prove this. All right. That's not, I mean, just do it term by term if you have to. I mean, you need to do that sometime in your life, maybe a few times. But this is extremely handy throughout all of theoretical physics, so do it. Okay, so once you have that, you can multiply pretty much any products of Pauli matrices. Just substitute this, then you're gonna, somewhere you're probably gonna have 2 epsilons crop up. You need those reduction formulas for pairs of epsilons. This is why you gotta do all the exercises in the book, right? You know, I give you things like this for exercises. You gotta be able to do it, okay? Yeah, on time, not like I was today. I was incredulous when I looked at the clock. I had to just stare at it for the longest time. 12:15. No, is the clock wrong? Okay, but do this for Wednesday, right? You know, it's not that long a problem. I mean, you know, you're unfamiliar. You got to prove a couple of relationships for Pauli matrices, so you know it could take, I don't know, an hour or 2. I'm not sure how long it will take. If you've worked a lot with Pauli matrices, you know, you can probably do it. Well, you can do it in less. But okay, so what are you going to get? You're going to get a relationship between these 3 real numbers x prime and those 3 real numbers x. And if you've done it right, you will know, because it'll be the same relationship we just derived for SO3. And that's how you do a rotation. And I have had engineers come to my office in the physics building and ask me, how do you do rotations with SU2? We want to put that on a computer. And I mean, you know, this is an easier way to do it, actually. You know, those n.j's are, you know, they're sort of messy. And get that same formula that we derived, that is a rotation. Now it's going to be a rotation by phi about the axis n. You'll need double angle formulas. And I'm always checking my email if you get hung up. So don't hesitate to just pop me an email. So what we get here is that the SU2, elements of SU2 can affect a rotation on traceless Hermitian matrices that represent real 3 vectors. Now think about tensors and general relativity here. What we're doing is we are representing a real 3 vector as a rank 2 tensor under SU2, right? Matrix, it's a rank 2 tensor. What are the rank 1 tensors? What are the vectors? And right, SU2 is, you know, it's a linear group. What's it acting on? There must be some objects. They're complex, so they act on some complex 2-dimensional space. All right, yeah, not the complex plane, a plane of complex planes. You know, that's a big space. But now these act linearly on those. So my A can just act on chi to give a chi prime. Just a simple vector transformation, 2 dimensions. Okay, it's complex. But now, you know, like, what's it doing to these guys? These guys are called spinners, right? And they, I don't know if you've gotten used to the idea of the term representation of a Lie group. We're talking about linear representations of a Lie group, which means that the Lie group, we're taking the Lie group to act on a vector space. All right, now what that means is that we're going to represent, you know, the things that act on a vector space and preserve the vector properties are matrices. So when we say a linear representation of a Lie group, we expect it to act on some vectors to give other vectors, and we do that with a 1-1 tensor, right? A transformation matrix. So these group transformation matrices, these are actually, you know, some 1-1 tensors. They're transformation matrices, and they're going to map spinners to spinners. And now if we, now let's just work it out. We've already got you deriving one of the most useful relationships. When you expand this out as the Taylor series for an exponential, you are going to get, you know, linear combination of sine phi over 2 and cosine phi over 2. Same way we did with the j's. So what happens to a spinner? E to the I phi over 2 n dot sigma acting on alpha beta is going to give what? This thing. So we're going to get alpha cos phi over 2 beta cos phi over 2 plus, right, that's the identity. Then we have to worry about right, sine phi over 2. Then we have this n dot sigma acting on chi. That's a matrix acting on chi. Right, so let's pick a rotation. Let's do a rotation around, say, the x-axis. All right, that means I'm going to choose n to be unit vector along the y-axis. And that means that this matrix is going to be 1, 1, and that's acting on alpha beta. And we have an I sine phi over 2 out here. And that's just going to interchange the alpha and beta. So sine phi over 2 beta alpha. So putting that all together, this becomes alpha cosine phi over 2. Then down here we have plus I beta sine phi over 2. And then the second component is going to be beta cosine phi over 2 plus I alpha sine phi over 2. This is the effect of a rotation through an angle phi about the x-axis on a spinner. Now, that doesn't necessarily mean a whole lot to me, you know, maybe even less to you, but let's look at one thing that happens here. Suppose we let phi equal 2 pi. What happens? Phi equals 2 pi, and this is going to become, okay, cosine 2 pi over 2 is cosine pi, that's minus 1. So we get minus alpha. Sine of 2 pi over 2 is sine pi, that's 0. So those go away. And here we get a minus beta. So minus alpha beta. The spinner goes to minus itself under a 2 pi rotation. Now, a 2 pi rotation of, well, when you get this final formula for x, it's going to bring you back to x, right? A 2 pi rotation in real 3 space brings you full circle. And you'll see that happen. You get double angle formulas when you work this all out. So you will see that if you put in 2 pi, x prime equals x. You can show that quite generally because a e to the I pi n dot x and n dot sigma. It's actually easy to work this out because it's equal to this thing. Yeah, all right, let me write this out. All right. E to the I pi n dot sigma is just identity cosine pi plus I n dot sigma times sine pi. Sine pi is 0, and it's just equal to minus 1. If I put minus 1 in here and here, the adjoint of -1 is 1, I get x equal x prime. So there's the proof for a 2-pi rotation, that a 2-pi rotation under SU2 returns a real 3 vector to itself. But it's clear that it does not return the spinner to itself. It returns it to minus the same spinner. Work out as many examples as you can squirrel away time for of, what rotations do to spinners. Rotate around the X, Y, Z axes, right? Do a bunch of that. We'll probably do a bunch in quantum too, quantum mechanics. But it's possible to develop a little bit of intuition about what rotations do to spinners. I can't claim to be very good at it. I've looked at a bunch of examples like this, and you get something definite, but you're working in C2. It's hard to picture C2, right? So instead of picturing C2, I'm thinking, let's go on to the Lorentz group. I see yeses and yeses. So we're good here. Only I might see a question or 2 or 3. So please, questions.
I have an Alex question, I guess.
Well, let's hear it. We'll see how long it takes.
It's not too big. So I guess I'm just wondering, because I just read in here that there's a 1-to-1, or we're kind of associating the determinant with the length of the vector. Is there a way to view some geometry in that we're like making like a bilinear form into a determinant or something?
Okay, so
an O2.
Okay, so we're talking about rank 2 tensors over C2. What's the determinant of those look like? Yeah, I'm not sure it's so obvious. I would say play with it. If you can now, okay, determinants are normally volumes, right? In 3 dimensions, a determinant is a volume of some sort of parallelepiped, right? So, maybe you can associate determinants in C2 with some sort of, I guess it would be a 4-dimensional volume. Try it. It's an interesting question. The more geometric intuition you can build up about these guys, the better. But I don't know the answer to that question.
I guess that picture, yeah, thanks, would be something like the normal vector squared could determine an area, and that's the same as saying that the determinant of a lower volume is that area.
Yeah, what you might do is try, writing some. I'm just looking at the chat. So the try unit vectors. Try some simple vectors. See what happens to those. Let's see. Yeah, you've got the triple product. Oh, hope we haven't lost Guillermo. The triple product gives a volume in real 3 space. What does that do under Pauli matrices? What do the SU2 transformations do to something like a triple product of real vectors? I mean, you could ask questions like that and try and see what the geometry is doing. Don't know. But for the Lorentz group, let's see what we can do here, because this is where it gets really nice. Let's now let sigma alpha be the identity and the 3 Pauli matrices. And what happens if we take a real 4 vector and contract it into those guys, where this will be the 0 component. So what we're talking about is now t plus z, x minus I, y, x plus I, y, and t minus z. And interestingly, all the same stuff works. Let's call this guy capital X now. And if I look at the determinant of this capital X, I get t squared minus z squared minus this times its complex conjugate is x squared and y squared. And that is the space-time vector length. That's what a Lorentz transformation has to preserve. Whew. Now what are we dealing with? What do we have to preserve now? We've dropped the trace condition. Now we can have a trace because the trace of this guy is 2t. That can be anything we like. So how do we characterize this matrix? Well, x dagger equals x. And we need to preserve the determinant that x prime has to be determinant of x because that's the line element. Not the line element. It doesn't have to be infinitesimal. It's vector length in space-time. So now we're down to just two conditions, and hermeticity is pretty easy. Take any A, act on X, act with a dagger. That's Hermitian. So we're good there. And the determinant, we get the same determinant condition. The magnitude of the determinant of A has to be magnitude squared 1. And as before, a phase is not going to do anything. So we lose nothing by taking det A equals 1. So, sorry, number 1. So now what? There's no other restriction on A. There's only one restriction on A, that its determinant be 1. What that means is that A is an element of, right, special because its determinant is 1, but otherwise the linear group in 2 complex dimensions. SL2C is the group nomenclature for that. So the general linear group in two complex dimensions then impose the unit determinant, that's SL2C, and those in the same way should generate Lorentz transformations. And I've given you an exercise for these guys too. The generators, we can write generators for SL2C pretty easily because they can be pretty much anything, right? If we have, let's see, all right, if G is an element of SL2C, and I expand it infinitesimally, I'm going to have 1 plus, well, really pretty much anything, right? The only condition I'm going to get, it's the same condition we had before, it's got to be traceless. So it can be traceless Hermitian, or it can be traceless anti-Hermitian. So linear combinations of sigma or I sigma span all of the traceless 2x2 complex matrices. And so what I want to do is identify the anti-Hermitian ones as rotations, because rotations always have anti-Hermitian generators, right? If we have a rotation with the J's, right? They're anti-symmetric, right? An anti-symmetric matrix is anti-Hermitian. It's real. So you only get the anti part. The dagger is just the transpose. So an anti-symmetric matrix is a real instance of anti-Hermitian. These guys always generate rotations. Then we have 3 more generators that have Hermitian generators. Now, so another homework problem. What's the exponential of these guys? E to the psi n dot sigma. Psi real now, right? That parameter is called the rapidity. And maybe you've seen boosts written in terms of the rapidity. So these are your boosts. Work them out. If you have questions, ask, but your Taylor series for n dot sigma squares to 1, right? That's not hard to show. So you're just going to get sines and cosines. You'll generate that formula that we had, but it won't have the I in it. So it's not going to have the alternating signs. What you're going to get are sinh and cosh. And sinh and cosh are, in fact, generators of Lorentz transformations. In the minute or two that remains, let's look a little bit at sinh, cosh, and boosts. All right, in a little two-dimensional toy space-time, vectors which have the same length are things like t squared minus x squared equals some constant, say 1. All right, so we're talking about hyperbolas that asymptote to the speed of light here. So, that's a horrible picture. Let me fix it. Put it in the speed of light here. So, right, unit hyperboloid looks like that. A boost preserves that hyperbolic norm. So a boost is going to take a vector like that and change it to a vector like that. And the geometry of hyperboloids, a unit hyperboloid, the components, the x and t components here are cosh of that arc length, let's call it psi, and sinh, psi. Now, if you'll see the relationship with the usual boosts if you let the hyperbolic tangent, sinh over cosh, be v over c. So you'll reduce to the usual gamma factors and all of that if you let tanh psi equal velocity over the speed of light. So you'll recover the usual form of Lorentz transformations of boosts if you exponentiate this and make those identifications. Okay, so ask me questions because I want you guys to work this out. I've worked this out a dozen times. I don't need to again. I'll do it for you if you get stuck, but I think you probably have enough to work this out, and it'll be some good learning. So ask me any questions if you're uncertain what to do. But yeah, show that these guys are boosts.
Is there a classical analog for that boost matrix then, that exponentiation without the imaginary? Is there a classical analog?
Oh, sure.
Yeah, what is it?
SO31. All right. This is a 2-to-1 cover of SO31.
So, sorry, yeah, I should have a better intuition of that. But what is an action of SO31? What would that represent? Like 3 is a rotation.
So we're talking about some 4x4 matrices that preserve a 3-1 signature inner product. And so if you expand those 4x4 matrices infinitesimally and impose the preservation of the the metric 3-1 inner product, you're going to find, right, the generators of SOPQ are always anti-symmetric when both indices are down. And that's true for SO3-1, but now to find the 1-1 generator, you need to use the metric like this. So these guys are always anti-symmetric because you use a metric to lower it and you just get, you know, this transpose condition. But when you raise this, if you raise a zero component, you're going to get a minus sign. And what happens then, the 0i transformations become symmetric, not anti-symmetric. And so you get some 4x4 generators that are three of them. So they're built from anti-symmetric matrices. The anti-symmetric in 4 dimensions. You've got 3 here, you've got 3 here, and these are all determined. So the general anti-symmetric matrix, there are 6. There are 6 Lorentz transformations. 3 are just spatial rotations, these 3 down here. Those are stay anti-symmetric, but when you raise an index, these guys become symmetric. Those are the generators of boosts. So take 0, 1, 0, 0, 0, 1, 0, 0, exponentiate that, and you'll find the usual, you know, gamma x minus vt, you know, gamma t minus vx over c squared. You find the usual form for the boosts. Okay. Good.
So
I guess this
what's
is, oh, go ahead, sorry, no.
so
Yeah.
what's new with this SL2C formulation than the SO31?
I gotta
What's
get
new,
going.
what's the new
but-
information?
Okay. Yeah, and yeah, I know. Okay, I'm still recording. So we'll keep talking. So check the recording.
Sounds
And
good.
yeah, and we'll Zoom. I don't know. Maybe we can Zoom tomorrow.
Either Thursday or
Thursday's good.
Friday works best for me.
Yeah. I'm good with. Yeah, actually Thursday's easier than Friday for me. So let's plan on Thursday afternoon.
Sounds good. Yep. Anytime after 12, I'm free on Thursday. So.
Yeah, perfect. Okay. Well,
right.
we'll email and set a time.
Yep.
Okay.
All right. Talk to you later.
See you, Eli. Okay, so we're asking what's the difference? SL2C it acts on two component complex vectors. Those are spinors. So we're seeing that the Lorentz group. So okay, you know, let's back way up historically and suppose in 1920 or so that see you, Lyle. Suppose that quantum physicists or classical physicists in 1880, suppose they knew enough group theory to know that SO3 has a covering group by SU2. Spinors are classical, right? You know, spin comes out of the group theory. It does not come out of quantization. It happens to be that we actually only see it physically in things that depend on Planck's constant, but it's actually a classical group theory result. The rotation groups and the Lorentz group know about spinors already. Now, something we're going to find. So these are 2 component spinors these act on, and that's spin up and spin down, electron. When we get to the Dirac equation, it turns out that we have to deal with 4 component spinors. So we're going to do this 2-to-1 construction in more generality. We can do the 2-to-1 construction for SOPQ. Right, SOPQ has a 2-to-1 covering by a group called spin PQ, and those are dependent upon Clifford algebras, and Clifford algebras are a certain, condition on matrix multiplication that actually is stringent enough that in order to satisfy it, the matrices have to be big. So in n dimensions, so if P plus Q is n dimensions, and we want to construct the 2-to-1 spin covering group of SOPQ, it turns out that you need complex vectors that are of dimension 2 to the n over 2. So if you want to do the covering group of the 10-dimensional Lorentz group, SO91, then the spinners are going to be of dimension 2 to the 10 over 2 is 2 to the 5th, 32 component complex vector space, right? You need 32 by 32 dimension matrices to act on the 32 component spinners. And when you break down to 4 dimensions by compactification or something, those 32 component break into 8 sort of normal Dirac spinners. But the dimension of these spin groups gets big. And that's the reason in supersymmetry that supersymmetry only exists in low dimensions, because you can show in a supersymmetric system that maps between bosons and fermions, you have to have equal numbers of bosons and fermions. The fermions are described by spinners, but the number of degrees of freedom quickly outstrips the number of degrees of freedom of your bosonic fields, which so far as our experiments go at least, and some strong arguments, only go up to spin 2. We don't see spin fields higher than 2. And so at the very least, you would need a whole lot of them, and therefore a whole lot more gauge bosons, a whole lot more fundamental interactions than we actually see if you wanted to do supersymmetry in even higher dimensions. You would be introducing huge numbers of fields that we don't see. So anyway, spin representations exist for every SOPQ. It's called spin PQ. They are of high dimension. There are general formulas that show we can do it. We can carry out a proof that they've got to be that size or larger. And actually, we'll do that for Dirac spinners. But yeah, I think before long we'll be writing out the Dirac equation and looking at properties of those spinners. Let's see. So what else can I show you here? SL2C. Yeah. So you guys know how to exponentiate this, because it's really just exponentiating the Pauli matrices with or without an I. So we get if you work out the Lie algebra of these guys, I probably do it in the notes, but I would call these like K's and these J's. I think I might have written that. So if Ji is I, sigma I, and K I is just sigma I, then compute J with J, J with K, and K with K require the structure constants, the constants that you get from the commutators, to be real. And you'll see, you'll get either an I or a J from the commutation relations. What you find is that a commutator of J with J is another J. They form a closed subgroup. The boosts do not form a closed subgroup. A K with K is a J. And that's actually what underlies the Thomas precession in atomic physics. The fact that you're really doing 2 boosts. If you boost to the, you're looking at a change in the rest frame of the electron as it orbits. So you have to boost to get to the rest frame of the electron, and then you boost again to see the change. And those boosts don't commute, so you get this anomalous precession, an anomalous rotation that wasn't expected before you actually did the relativistic version. But works out just right. Thomas precession, I think, is what that is. I probably have notes on it somewhere. Maybe we can look at that at some point. Other questions? what can I clear up here? Yeah, Kevin.
Just saying see you later.
Oh, okay. All right.
Yeah.
Yeah.
See
I
ya,
guess I had
Guillermo. You headed off to Guillermo, or you
more about the.
Okay. All right.
Yeah.
You're welcome.
Bye-bye.
Okay.
I'm just asking
bye.
Silly. You can hang out if you want to, Guillermo. But
Let's hear.
yeah, I guess so I guess I can see the representation of a PQ group through the metric. Is there a more classical way that those matrix show up? Like does a PQ metric like does that group, is there something else that could represent? Like is that a represent? I want to say it looks like a sync equation. That's the gut says that you set S equal to 0 and it looks like a sink in a source of sorts. So I'm curious.
S, what are you setting to 0? What S you think?
So just if you set just for what light experiences, right? It sees zero space. So in some senses, time is a source for space for something moving at the speed of light. So like that's a wave hand. That's a handy wave. Don't worry.
Yeah,
But
no, I'm not quite sure what you're saying here.
I guess I'm asking if there are any like not metric ways to interpret like PQ groups. Like is there another?
So like, yeah, something that depends on a PQ metric. So
I guess.
so we're talking about matrices that have P1s and Q minus 1s. Like that.
Yeah. Yeah.
So when we talk about SOPQ, we're asking about transformations that preserve like an inner product with that, right?
Yeah.
So we would have like x squared minus y squared as some constant. So yeah, if you have something that does that, well, I don't know of many applications of that. One that comes up is the conformal group of spacetime. So spacetime preserves the 3-1 metric, but the conformal group of spacetime, if we add sufficient points inverse to the light cone at the origin, so it's compact, then the transformations that preserve that are the transformations that map light cones into light cones or preserve infinitesimal line elements. Any of those describe the conformal group. You'll find it's SO42. So you actually have Q as 2 in that case. Yeah, basically you have Lorentz transformations that preserve this part, and then let's see, then you have two, let's see, what is it? Wait, what am I preserving here? Yeah, oh, six, the thing you're preserving. Yeah, you actually write this
-1
off diagonal. So this, if you diagonalize this, it would be a 1 minus 1, and that gives the second time-like direction, right? Putting it off like this makes the translations and co-translations have the right commutation relations.
That's in Jordan form then, right? I think, or I guess there's a lower diagonal.
Oh, well, yeah, except this one you can diagonalize. So it is
Right.
open to and preserves, 2 minus signs and 4 plus. Just to identify it with the usual way of identifying conformal transformations. So conformal transformations, let's start with the Poincare group because we know that preserves the line element. The thing there are two things you add, and in order to add it, you need to compactify the space. You have inversions, and if you translate an inversion, let's see, let me back up and say this. You add 5 things when you allow allow ds squared to transform with a factor. The just dilatations, you can rescale everything. But the other thing is if you invert and translate and invert again, it's another kind of translation. You have two patches, right? You have two patches on a compact set. So you can do a translation of the point in infinity, and what it does around the origin looks pretty messy. You can translate at the origin, and what it does at infinity looks pretty messy, but they're, you know, completely dual to one another. So you get two different sets of translations. You get translations of the point at infinity, you get translations of the origin. They each commutes among themselves, translations commute, but the commutator of the two gives you actually Lorentz transformations and dilatations. So that doesn't vanish.
Because you have a two-dimensional symmetric subspace now instead of a one-dimensional. So to do the Poincare translation, which is also symmetric, you're doing it with respect to both basis vectors. So you're in the conformal Brook, you do okay. So one is a translation with respect to like time, but at the origin, time equals 0, and then one is with respect to spatial infinity. One is respect to infinity. One's respect to
the space-time origin and its inverse.
So yeah, is that inverse? Is that spatial infinity, or is that
it includes spatial infinity, but no, you got to be careful because you define inversion by inverting through a sphere, which is really a hyperbolic. But so I can define the inverse to most space-time points this way, but I run into problems at the origin and on the light cone. So what I do is, right, in order to add those points, right, as x goes off to infinity, this guy's going to 0.
Yeah.
So the points I need to add are points on the light cone at the point at infinity. So if I look at the limit as this x goes to the origin, that gives me an origin in a coordinate patch at infinity. And I add that point, I add y equals 0. And then if I'm on the light cone of the origin in space-time, I add the light cone of the point at infinity, and that compactifies the whole thing. You can, with a little playing around with, it was actually simple pictures, you can carry a curve off, go to the new coordinate patch, continue the curve on around, come to another coordinate patch after you pass the light cone and get back to the origin. So you show that curves, you know, any curve you choose, you can continue right through that infinite light cone and back to the origin, or back to the normal space-time.
Fascinating. So then, okay, so the infinity is just proper propagation of light. It's the boundary of the light cone. It's that's what infinity, the boundary of the emanating light.
Yeah. So add a point inverse to the origin.
Yeah.
And add its light cone.
Okay.
And on that space, you have 15 transformations that preserve a 4-2 metric.
I'm sorry, it's the light cone. Okay, sorry, it's the light cone of spatial infinity. What do you mean by the inverse of the origin? Pardon me again.
Okay, x equal y equals z equal t equals 0. Right. Okay. So the space-time origin, t equals 0, x equals 0. And now I want to add an inverse to that point. So I can get there. I can actually get there in most any direction. But yeah, so I define a new coordinate that I can you know, I could travel up the time axis to it, right? I could travel out any direction, and as this x approaches the origin, these guys become very small.
Oh.
So I'm going to add the point where y becomes 0. And that corresponds to this x going to infinity.
Mhm. Yeah, okay, I'm sorry. I forgot that this is a 4 component. You're not dividing by a 3 magnitude. This is a 4
No, that's really, yeah, that's the 4 vector length.
So does the, wait, so does the, do dilations then, like, do they affect the parameterization of light? Like when you do the parameterization of the light cone, will that, if you do a conformal dilation, does that affect what you're?
Yeah, so a dilatation, I'm just multiplying by a factor.
Mhm.
Like that. So the light cone stays the same. That's 0, you know, that's the same as lambda squared.
Right. If
It's still 0. So the light cones map to themselves.
But if we had parameterized its path by a lambda, picked a lambda, and then we dilated, it would change the lambda to a lambda prime. Am I reading that right?
Oh, if
In our we'd have to,
if we look in the y coordinates. So yeah,
yeah, in the y
you can ask, you know, so this transformation is an inversion of yeah, x going to this point is called an inversion. And I can ask if I get anything new if I do an inversion followed by say a dilatation followed by another inversion. And the answer is no, I don't get something new. It's just some d prime, right? So if I let this act on x mu, that's going to be inversion on dilatation on x mu over x squared. That dilatation is just going to scale it by something. Well, if x goes to lambda x, then this is going to go to 1 over lambda x mu over x squared.
maybe down. Yeah, thanks. Okay.
Yeah. And if I invert that again, I'm going to get x mu over lambda x squared over magnitude of that is x squared over lambda squared x squared squared. So let's see, that ends up giving me
Yeah.
yeah, what do I have? That ends up giving me lambda x, I think, doesn't it? 1 over lambda, so I'm lambda squared, x squared, the x squared cancels. Yeah, that just takes me back to lambda x. So it doesn't do anything different. Now, if I do the same thing with a Lorentz transformation, that also just gives me a Lorentz transformation. But if I do it with a translation, now I get something new. That's what gives me the special conformal transformations, which I think of them as co-translations, but that hinges on a particular understanding of how to do conformal gauge theory.
Yeah.
But yeah, these are just translations of the point at infinity. Y goes to y plus a constant.
So is this association with infinity happening exactly because it's 4-2? And so just by having a dual form where there's 2, that we have just a natural association with 0 and infinity. Like if it was 4-3, would you not be able to make the association at infinity? Like there'd be a, I don't know, it would be like a 3, there'd be like a 3 symmetry.
Let's see. Yeah, and the conformal group of spacetime is SO42 or spin 42, right? Now, you know, we can ask about the conformal group of any orthogonal group. So if we have a PQ metric, so a PQ metric, then that's preserved by SOPQ, if we compactify that PQ space and ask for its conformal group, it's always SOP plus 1, Q plus 1. So it always adds 1 to each. So yeah, you're, let's see. Well, yeah, various ways to prove that. But so, you know, you can get to, you know, higher Q that way, one higher. I can't think of any other immediate applications of SOPQ. You know, usually Q is 0, 1, or 2 for the physical applications, that at least the ones I've run across. I mean, you know, in engineering, you could come up with some hyperbolic something or other, I suppose.
Yeah,
You know, just some complicated problem might encounter that. But in terms of fundamental physics, I don't know of another example.
Yeah, I think that's what I'm trying to get at, is just a silly physical system to model PQ off of. And so this conformal dilation, this helps a lot with the PQ. Q doesn't equal 1, this picture, at least when it equals 2. I'll just kind of keep fishing. Yeah.
You know, when I was teaching at Swarthmore, I had some undergrad students do a project saying, you know, what would happen if you know, it was space-time time, if you had 2 time-like dimensions.
Yeah.
And, you know, draw pictures of that. And, you know, I mean, you can have closed time-like loops, right? Right. So you move in a plane, a time plane, which means you can turn around and come back, right? So that's fairly weird. And, you know, you can draw all sorts of, you know, pictures and try and track the light cones. But, you know, it doesn't correspond to any physics that we routinely see. You know, I don't know, maybe in Utah, but you know.
Yeah, I don't know what goes on here. Yeah, I read Penrose's An Elegant Universe forever ago, and that was one of the interesting things that he put in there, was that like just different space times with different types of time, like dimensionality versus how many time dimensions you got. And there's there's interesting bounds that at least he was putting in there, like you have if you put too many time dimensions within too little space dimensions, things are unstable. And I'm trying to get, it's kind of interesting how that computation was made.
Yeah.
But
that's interesting. Stability. Yeah. So yeah, things could evolve into their own paths. So if you have something that seems like a stable system, you know, it can come back and affect itself, right? So in terms of our ordinary notions of causality, it could be very strange.
Yeah, I can't remember what the criteria was. It's been forever. I could maybe look it back up, but I think it was even something like can't exist, like time loops, even if we allow causal. I think it was some weird, like, I have no idea what he was doing on, but anyway, that's kind of what instigated all this. Is I know that there is a way to higher PQs. And I in the back of my mind knew that Penrose has said that these are 2 time dimensions. So I'm kind of playing. So sorry.
Yeah. Yeah, you know, you can play with it, but you know, it does depend on the interpretation. You know, there's certainly no problem with having 2 time-like dimensions in the conformal group, because the basic space you're working on is still a 4-dimensional space-time, and let's see what happens. You don't experience that extra time-like dimension as a time-like thing. It gives you scale invariance,
which is I think that's the fascinating interpretation. Then is these extra.
What am I thinking of? you know, I know some very physical spaces that have zero signature, equal numbers of P's and Q's.
Oh, okay. Uh-huh.
All right, a biconformal space.
Oh, yeah.
So
Right. Yeah.
yeah.
Cool.
Uh,
No.
so okay, so here's the construction. I probably showed you this before. I will probably show you again.
I've certainly forgot it before, so I'll forget it again.
So what
No.
we want to do is build geometries that respect the known physical symmetries. And Cartan gives us some really nice tools for constructing spaces with any sort of symmetry. So we know how to do that. Right, well, we know we have dilatational symmetry because we can choose arbitrary units, right? You know, I can choose centimeters or no, change the meters, and now I'm going to divide everything by 100, right? I can do that, and I can do that locally as well. I can use redshift for cosmological time, right? There's a nonlinear mapping, but monotonic between time and redshift. So, you know, perfectly good time coordinate. So if we build models that respect that, those are things that we need to allow transformations that allow dilatations, that allow preservation of ratios of lengths or ratios of infinitesimal lengths. Now, the things that preserve ratios of space-time lengths are Lorentz transformations and dilatations, period, a 7-dimensional group. If you preserve ratios of infinitesimal lengths, now you add translations and inverse translations. All of those become possible. That's the conformal group. Now, if I take a quotient of the Poincaré by the Lorentz group, right? That gives me Lorentz fibers over space-time. All right, that is a manifold with local Lorentz symmetry. And if I generalize that, I can, there's this straightforward procedure that lets me build every Riemannian geometry that I like by just generalizing the connection on that fiber bundle. So, but now we recognize that we really should be considering conformal transformations. And we can take the quotient by what? Well, we know that we know that these fibers ought to include dilatations because we can choose local units. And that's the homogeneous veil group. So if I take the quotient here by the homogeneous veil group, what I get is an 8-dimensional manifold with homogeneous veil fibers. That's a biconformal space. And then I curve this guy. And it turns out that the things that are acting like translations here are the translations and the co-translations. And they're, you know, we've maintained those on an equal footing. There's a natural metric on this, which is it comes from the killing metric, right? The killing form is non-degenerate. If I work out the killing form for the conformal group, it's something like this for the Lorentz transformations, non-degenerate for Lorentz. Then we have translations and special conformal transformations and dilatations besides P and K and D. Now, if I look at just the Poincaré group, those guys commute with one another and I get 0. If I look at just the special conformal transformations, well, just put my origin at infinity and it's still the Poincaré group, I get 0 here. The K's commute with one another. but the P's and K's don't. And what I find is a Kronecker here and a Kronecker here. And then the D's down here give me a 1. So, so the killing form for SO42 is non-degenerate. And unlike just the Poincare group, so one thing that would be lovely with the Poincare group is to say, oh, you know, I've done this group quotient. Does it naturally give me an inner product for orthonormal frame fields like the Minkowski metric? But the answer is no, because the killing form is 0 there. But if I ask the same question in a biconformal space, the answer is yes, because this matrix as a whole is non-degenerate. So if I project that onto the base manifold as the inner product of my basis forms, like that, then okay, the geometry tells me what the inner product is, and notice it's traceless, right? So even if I diagonalize this, it's traceless, right? So it's P equals Q. So it's so if we started with, you know, space time, that's going to be a 4-4, an SO44 invariant thing.
Okay. Yeah. And so that's why this is, nope, that's a silly question too. Okay, yeah. Okay, so that's kind of so is that why this is being used in like supersymmetry and stuff? Because like there's these two quote unquote time parameters that are in each copy of the space, but really in one space, one is being viewed as this conformal measure where you're getting this, that it's being represented in this as this conformal group in either, but with a PQ, there's also two. No, I'm saying this is stupid. I'm saying I think this is a wrong thing, but I'm seeing the picture you're drawing. This is fascinating.
All right. So
sorry. Yeah. Sorry.
Yeah, no, okay. So so this is a PQ space. So I could choose like any slice of this, and I can get any signature I want. Right. So if I look at, you know, if I've got an 8-dimensional biconformal space, I can find a 4-dimensional, say a Lagrangian submanifold. These things are symplectic, it turns out. There's a symplectic form, there's complex structure, they're Kähler, you know, they're everything you could ever want. But the, you know, there are, you know, 4-dimensional submanifolds with any signature, you know, 4, 0, 3, 1, 2, 2, and so on. So
yeah, okay, yeah. I think what I was trying to say is that there's some canonical splitting, maybe is what I'm trying to say. But that, okay, that's a good point. Yeah, there's any combination as a submanifold. Okay.
Yeah. So here's an example where P and Q can be anything we like. Yeah, and you know, this happens regardless of what you start with. So if we're, you know, if we took any, if we take any SOPQ symmetric space, compact to find it, find its conformal group is going to be SO P plus 1 Q plus 1. And now if I take that conformal group over its Veil subgroup and look at the killing form, you know, the killing form is going to be SONN symmetric, P plus Q equals N. It doesn't matter what we start with here, we always get NN for the biconformal space.
That was, and oh wait, sorry, this matrix down here, this that we boxed out down here with PKs and dilatations. This is the general group. This is the general action, right? And then when we're modding, yeah, we're just looking at sub manifolds in this action, right?
So this is basically the killing form for SOPQ up here. But the translations, you know, this box is n by n.
Yeah, and this is,
and it's traceless.
and that's the SONN.
So this induced metric has SONN symmetry.
Yeah, fascinating. Okay. Oh, yeah. So that's the, and that's the, is that where the, is that dial, no, I'm being, that we were just talking about in class. Is this boost? Would this be in the conformal group? Would this be the boost sec? No, I'm being stupid because that's in the top left section. Okay.
Yeah, the boosts are up here.
Boosts are up there. Yeah.
Yeah.
Okay. Cool. So okay, that's the picture I'll try to work towards, is viewing SONN as the Poincare and special conformal subsector of the killing form.
That's right. That's exactly right.
That's fascinating. So it's like that's looking like that sector's looking something like translate at 0, invert, or no, sorry, invert, translate, invert back.
Yeah. Yeah, that's the way I got to this. I was looking at different ways of gauging the conformal group. And yeah, there are other ways. You can take other quotients that give you like something that looks like space-time, only there is no, you have vanishing projected killing form, but you know, you can, your connection still respects Lorentz, is still Lorentz. So you can use that metric anyway. But the problem was, you know, I originally thought that the special conformal transformation gauge field ought to do something interesting, like, you know, give rise to, you know, some other known interaction, electroweak or something like that. And, you know, maybe ultimately it does. But the thing that happens if you just do the 4-dimensional quotient is that the special conformal transformations, the gauge field for those always comes out to be essentially the Ricci tensor, and its trays and Ricci scalar in just the right combination that when you look back at the conformal curvature, it turns it into the veil curvature tensor. Right, so it subtracts exactly the right combination. So it enforces the curvature being the conformal curvature. It's really kind of cool how that happens, but it doesn't give you anything new. So I hit on this quotient as a way of keeping them from going away, right? Keeping those extra new gauge fields from being auxiliary, and by putting them on the base manifold, keeping them equivalent to the regular translations. I mean, they're all translations after all, right? Yeah. So keeping the symmetry between the P's and the K's into the geometry you build actually gives you phase space instead of just space-time. This guy's got a symplectic form.
Because instead of treating the conformal degrees of freedom as a gauge degrees of freedom, you've treated them as a base manifold degrees of freedom. You treat it as an
you end up breaking that symmetry, but you've increased the number of degrees of freedom of fields on the space. Yeah. So now everything, you know, every one form has 8 components instead of 4. So you have and you've got 8 coordinates instead of 4. So you have much more general functions. You have a lot more and more complex fields that you're dealing with.
Okay, that's
Yeah.
a really cool technique too. Again, that's another picture. That's another cool picture to be watching out. The duality between a gauge field and just its base space itself. That's another picture I don't. When you treat the gauging like you've done here, when's it useful to treat the gauging as a real thing as opposed to just using it as a gauge field on top of another?
You look at all possibilities.
Yeah. Okay.
Okay.
Cool.
So what I did ages ago was I knew I wanted to build quotients of the conformal group. You know, the quotients you take to build the manifold are going to be quotients by some subgroup. It's clear that that subgroup has to include Lorentz transformations and dilatations because those are manifest symmetries of nature. So the only two subgroups that actually respect those symmetries are the Veil group of those two alone, or you can add in one of the translations. So you can have a Poincaré version of the Veil group. So inhomogeneous Veil symmetry. So Lorentz transformations, dilatations, and one or the other translation, doesn't matter which. And if you take the quotient of the conformal group by that, you basically get Veil gravity. You get a four-dimensional space that's got, well, let's see. If you demand full conformal symmetry of your action, it's got to be something like the Veil curvature squared, and you're doing Veil gravity.
Yeah. Okay. Because just like you said, it was that the far field curvature is exactly the Veil curvature tensor.
Of far field. Well, by the time you write some general covariant action, right? Now it needs to be in that case it needs to be quadratic in the curvatures, but you write like the most general thing you can that's quadratic in the curvatures. You vary it, and now you've got these extra gauge fields from the special conformal transformations. You find that those are equal to, it's actually the Schouten tensor. It's a combination of the Ricci and the Ricci scalar, such that when you put that back into your action, whatever you had there reduces to the action for Veil gravity, the conformal curvature squared.
Okay, so yeah, and so in that case, the dilatation, the special conformal group is in some senses taking out the I just lost what I was going to, the trace of the Ricci curvature. So the dilatations, when you find the minimum, the dilatation field is reorienting itself so that I just had it. So that the curvature scalar is 0.
Yeah, here, let me show you a cool way to write it all.
Sure, because you're like parameterizing time to have unit always. Time is our light. You're parameterizing light to have unit always, right? I guess.
Yeah. So if I write RAB is, let's see, I usually normalize this with an n-2, but Ricci minus over twice n-1.
Do you mean Veil on the left side? Okay, I'm with you. Yep.
So that's just Ricci and Ricci scalar. So it's just a different combination. This is invertible, so you could use one or the other. But then if you take, let me define this symbol. It's just an anti-symmetric projection. So that's an anti-symmetric projection on 1-1 tensors. Then if I write, then I can write the Riemann curvature as the traceless, its traceless part plus, I forget plus or minus, but delta ACDB, this R, C, better make that an E. And let's see, something like that. Probably, let's see, need to anti-symmetrize. I'm used to writing this as a differential form. So anti-symmetrize CD.
Oh, yep. And sorry, the curl R is this other tensor you mentioned before? Yeah, sorry.
This is this guy.
You said it had a name. What was the, it has a name, right?
Scope.
Yeah, the scope. Okay, yeah, okay, cool. Cool.
Yeah, so as two forms, this is just RAB is CAB with the appropriate sign. I think you need a 2 here, actually. Or you're right, this is the 1 form. So you put a so you're right, that thing is 1 form, and then it's a lot more compact. So yeah, this is a nice way to write the relationship between the Riemann and the veiled curvatures.
And then that second term is going to be, that's going to be something like the conformal, the special conformal.
If you expand that out, it's exactly what subtracts all the traces.
Yeah, okay. Mm-hmm. And then that's the term that shows up when you write in a special conformal action and vary it.
Yeah.
That's
so you get two gauge fields. The translations are dual to the solder form. The special conformal transformations are dual to one we might as well call F, but that turns out to be essentially that guy. When you solve the field equations, it always happens. Almost anything you do, that happens. And when you put, so let's see, what is it? Yeah, we talked about Maurer-Cartan equations.
briefly. I know it's the locally flat space basis, but I'm probably
So what you have.
Oh, yeah, sure. Oh, dang.
So, and then when you generalize, you get some curvatures like this. So this first part would have been the Riemann curvature. When F turns into R, this guy becomes C. Right, so yeah, so you see you've got the same form here.
Okay, that's fascinating. Okay, well, that's a lot to chew on.
Okay, go chew.
Yeah, but that's.
Yeah, and work out those problems.
Yeah, I will. Good. Cool.
Okay.
Thanks, Professor.
You bet.
Okay, and when's our homework? I mean, I have our homework done. Do you just want that whenever then, or?
Let's see. So, yeah, just send me a photo of it or whatever. Or how are you doing? You doing LaTeX?
I was talking about quantum mechanics too, because I'm silly. I would probably just do them by. I could type them up if you wanted to. It's no problem. But I've just been doing them by hand.
No, that's fine. Just take a picture and email it to me. That's fine.
I have my thing. I'm easy peasy. I'm the cheater. I'm the cheater that was like.
You're just email me some sort of copy.
I mean, do you want us to be turning in homework for this class, or do you just want it to be do it because we're adults? Well, quote unquote.
Yeah,
for some of us.
somewhere in between. If you really have a question, you're stumped on a problem.
Good. Okay.
Definitely, send me that. Show me where you're having trouble. I'll look through.
And that's throughout any of the texts, not even the ones you assign, right? Just
Yeah. So any of the exercises that I've put in the book, either, know how to do them. If you've done them before, you don't have to do them again if they're familiar. But if they're not, work them out. Most of them are just exercises. It won't take you that long. But, at some point, I'll probably give you a real problem. And you need to be fluid with the exercises, right? So, for example, we're going to, I'm pretty soon going to talk about Dirac matrices. So spin 3-1 rather than SL2C, there's a 4-dimensional representation of a complex representation of the Lorentz group, and that's going to lead us to Clifford algebras and some 4x4 matrices, the gamma matrices, and by the end of the term, you need to be able to take a trace of a product of 8 gamma matrices. So, that gets long. But if you want to work out like electron-positron scattering or something, you're going to be taking traces of products of gamma matrices. So you need to be fluid with them. Okay.
cool. Well, and thanks again for the lecture today, because that's really helped me with the joint representation. So
Good.
I'll keep at it, and I'll probably have a lot more questions coming up. So
Yeah, I count on it. Yeah.
Great.
Okay. I'll see you, Alex.
have a nice day, Professor.
You too. Bye.
Bye.